NENOMATICA, where mathematics meets YouTube excellence. Welcome to this video on factoring a complex algebraic expression using the difference of squares identity. Today, we'll be working through a step-by-step factorization of this expression. Let's start by taking our expression, ab times a minus b plus bc times b minus c plus ac times c minus a. First, let's expand each term to see if we can find a pattern. For the first term, ab times a minus b expands to a squared b minus ab squared. Similarly, the second term bc times b minus c expands to b squared c minus bc squared. And the third term, ac times c minus a, expands to acc minus aca, or ac squared minus a squared c. Let's put these together to get our expanded form. We need to rearrange the third term to be consistent with our factorization approach. So let's rewrite the third term as ac times c minus, which gives us acc minus aca. This gives us ac squared minus a squared c. Now we'll reorganize these terms to prepare for factoring. Let's rewrite our expanded expression to group the terms differently. We'll write it as a squared b minus ab squared plus b squared c minus bc squared plus ac squared minus a squared c. Let's rearrange these terms for better factoring. Let's now rearrange the middle term by swapping the order. We get a squared b minus bc squared plus negative a, b squared plus b squared c plus ac squared minus a squared c. This gives us a squared b minus bc squared minus ab squared plus b squared c plus ac squared minus a squared c. Now, we'll try to factor out common terms from each group. Looking at the first group, we can factor out b to get b times a squared minus c squared. For the second group, we can factor out b squared to get negative b squared times a minus c. And for the third group, let's rewrite it as negative ac times a minus c. Let's combine these factored expressions. We now have b times a squared minus c squared minus b squared times a minus c minus ac times a minus c. Now, an important step is to recognize that a squared minus c squared is a difference of squares, which can be factored. Using the difference of squares identity, a squared minus c squared equals a minus c times a plus c. So our expression becomes b times open bracket a minus c times a plus c close bracket minus b squared times a minus c minus ac times a minus c. Looking at our expression, we can now see that a minus c is a common factor in all three terms. Let's factor it out. This gives us a minus c times b times a plus c minus b squared minus ac. Now, let's expand the expression inside the bracket. We have ba plus bc minus b squared minus ac. Let's regroup these terms to see if we can factor further. Let's regroup the terms as b a minus b squared plus bc minus ac. Now, we can factor the first pair as b times a minus b, and the second pair as c times b minus a, or negative c times a minus b. We now have a minus b as a common factor in the bracket, so we can factor it out, a minus c times a minus b times b minus c. And this is our final factored expression. Let's verify our factorization by multiplying back. Actually, I'll leave the verification to you as an exercise. You can expand the factored form and check that you get back our original expression, a b times a minus b plus bc times b minus c plus ac times c minus a. Let's look at our example. We need to factorize the expression x cubed times the quantity x squared minus 7 squared minus 36x. Let's begin by expanding the squared term. We'll use the perfect square formula, which states that the square of a binomial a minus b equals a squared minus 2a plus b squared. So in our case, x squared minus 7 squared equals x to the fourth minus 14x squared plus 49. Let's distribute x cubed through the parentheses. We'll apply the distributive property, which says that a times the sum of b and c equals a times b plus a times c. When we distribute x cubed, we get x to the 7th minus 14x to the 5th plus 49x cubed minus 36x. Thinking face, let's continue by factoring out the common factor x from all terms. We'll use the common factoring rule, which states that if x is a factor of each term in an expression, we can factor it out. So factoring out x gives us x times the quantity x to the 6th minus 14x to the 4th plus 49x squared minus 36. Let's look more carefully at the expression inside the parentheses. we can rewrite x to the 6th minus 14x to the 4th plus 49x squared as a perfect square. This is actually the square of x cubed minus 7x. To verify this, let's expand the square of x cubed minus 7x. We would get x to the 6th minus 14x to the 4th plus 49x squared, which is exactly what we have. So our expression becomes x times the quantity x cubed minus 7x squared minus 36. Let's recognize another pattern. We have a difference of squares in the form of squared minus b squared, which can be factored as a minus b times a plus b. In our case, we have the square of x cubed minus 7x minus 36. But 36 is 6 squared, so we actually have the square of x cubed minus 7x minus the square of 6. Using the difference of squares formula, we can rewrite this as x times the quantity x cubed minus 7x minus 6 times the quantity x cubed minus 7x plus 6. So our final factorized form is x times the quantity x cubed minus 7x minus 6 times the quantity x cubed minus 7x plus 6. Let's summarize what we've learned in this factorization problem. First, we expanded the squared binomial using the perfect square formula. Then we distributed the x cubed and factored out the common factor x. Next, we recognized that part of our expression was actually a perfect square. Finally, we applied the difference of squares formula to complete our factorization. Remember that recognizing patterns like perfect squares and difference of squares is key to successful factorization of complex expressions. Let's start with our example. We need to simplify this algebraic expression by applying various algebraic identities and factoring techniques. Let's begin our step-by-step solution. In step 1, we'll use the difference of squares identity to rewrite a squared minus b squared as a minus b times a plus b. This means we're transforming a squared minus b squared into the square of the product, a minus b, a plus b. For step 2, we'll apply the rule for squaring a product, which states that the square of a product equals the product of the squares. So we expand the square of a minus b, a plus b, to get a minus b squared times a plus b squared. In step 3, we'll use algebraic grouping to reorganize our expression. We want to highlight that we have a minus b squared appearing in multiple places. So we'll group terms to factor out common expressions. Let's rewrite this as a minus b squared minus 1 plus a plus b squared times 1 minus a minus b squared. For step 4, we'll use the property that a minus b equals negative 1 times b minus a. We notice that a minus b squared minus 1 is actually the negative of 1 minus a minus b squared. So we can rewrite our expression to show this common factor. In step 5, we'll factor out the common expression 1 minus a minus b squared from both terms. By applying the distributive property, we can write this as 1 minus a minus b squared times the quantity negative 1 plus a plus b squared. Finally, in step 6, we'll rewrite negative 1 plus a plus b squared as a plus b squared minus 1 to give our expression its final form. Our result is the product of two factors, 1 minus a minus b squared and a plus b squared minus 1. Let's summarize what we've learned in this video. We started with the expression a plus b squared plus a minus b squared minus a squared minus b squared minus 1. Applied the difference of squares identity to rewrite the expression, used the rule for squaring a product, group terms to identify common factors, factored out the common expression 1 minus a minus b squared. Rearranged to get our final factored form, this problem demonstrates how applying algebraic identities and factoring techniques can help simplify complex expressions. For further practice, try simplifying similar expressions with different algebraic identities. Key insight was recognizing the common factor 1 minus a minus b squared appearing in different parts of the expression. We can rearrange our expression as xy squared minus c y squared plus cx squared minus xc squared plus yz squared minus yx squared. Now that we've grouped the terms, let's factor each pair separately. For the first pair, xy squared minus z. Y squared, we can factor out y squared, giving us y squared times the quantity x minus c. For the second pair, zx squared minus xc squared, we can factor out xc, giving us xz times the quantity x minus c. For the third pair, yz squared minus yx squared, we can factor out y, giving us y times the quantity z squared minus x squared. In the third pair, we have the difference of squares z squared minus x squared. We can apply the difference of squares formula, which states that a squared minus b squared equals a plus b times a minus b. So z squared minus x squared equals z minus x times z plus x. But we can rewrite this as -1 times x minus c times x plus c to match our common factor x minus c that appears in the other terms. Now that we have the same factor x minus c in all three terms, let's factor it out. We'll combine all our terms, y squared times x minus c plus xc times x minus c minus y times x minus c times x plus c. We can now factor out x minus c from all three terms to get x minus z times the quantity y squared plus x z minus y times x plus c. Let's expand the expression inside the parentheses to simplify further. The term y times x plus c expands to yx plus yz. So our expression becomes x minus c times the quantity y squared plus x z minus yx minus yz. Today, we'll look at a special technique for factoring the sum of two perfect squares. We want to factor the expression x to the fourth power plus 64. Let's think about what this expression represents. We know that to factor this expression, we need to find a pattern. One approach is to recognize that this is a sum of squares. We can rewrite x to the fourth power as the square of x squared, and 64 as the square of 8. So our expression becomes the square of x squared plus the square of 8. Now, we might think we're stuck because a sum of squares doesn't directly factor. However, there's a clever technique we can use. If we look at the identity on the board, we can see that a squared plus b squared equals the quantity a plus b squared minus 2ab. We can use this to rewrite our expression as the square of the sum of x squared and 8 minus the square of 4x. Let's simplify this further. We can rewrite 16x squared as the square of 4x. Now, our expression is in the form of a difference of squares, where we have the square of x squared plus 8 minus the square of 4x. Now that we have a difference of squares, we can apply the formula a squared minus b squared equals a minus b times a plus b. In our case, a is x squared plus 8 and b is 4x. So we get x squared plus 8 minus 4x times x squared plus 8 plus 4x. Let's simplify each factor to put them in a more standard form. Let's start by understanding the problem. Given that a and b are natural numbers that satisfy the equation a plus b equals 3,598, we need to find the value of the absolute value of a minus b. Let's solve this step by step. Step 1. We begin with our given equation. A plus b plus ab equals 3,598. Step 2. Let's factor b out of the last two terms. We'll use the distributive property of multiplication over addition. We can rewrite the equation as a plus b times the quantity 1 plus a equals 3,598. Step 3. Now we notice something interesting. We can rewrite as 1 plus a minus 1. So equals 1 plus a minus 1. Substituting this into our equation, we get 1 plus a minus 1 plus b times the quantity 1 plus a equals 3,598. Simplifying, we get 1 plus a plus b times the quantity 1 plus a minus 1 equals 3,598. Now, let's add 1 to both sides of the equation to prepare for factoring. 1 plus a plus b times the quantity 1 plus a equals 3,598 plus 1, which equals 3,599. Step 4. Now we can factor out the common term 1 plus from the left side of the equation. Using the distributive property again, we get the quantity 1 plus a times the quantity 1 plus b equals 3,599. Step 5. Now we need to find values of a and b that satisfy this equation. Let's try to factor 3,599. Notice that 3,599 is very close to 60 squared, which is 3,600. So we can rewrite 3,599 as 3,600 minus 1. Using the difference of squares formula, we get 3,599 equals 60 squared minus 1 squared, which equals the quantity 60 minus 1 times the quantity 60 plus 1, or 59 times 61. Step 6. Now we can equate our factored expressions. The quantity 1 plus a times the quantity 1 plus b equals 59 times 61. Since these are products of integers, and both factors must be positive because a and b are natural numbers, we have two possibilities. Case 1, 1 plus a equals 59, and 1 plus b equals 61, which means a equals 58 and b equals 60. Case 2, 1 plus a equals 61, and 1 plus b equals 59, which means it equals 60 and b equals 58. Step 7. Now we can calculate the absolute value of a minus b for both cases. For case 1, the absolute value of a minus b equals the absolute value of 58 minus 60, which equals the absolute value of negative 2, which equals 2. For case 2, the absolute value of a minus b equals the absolute value of 60 minus 58, which equals 2. We see that in both cases, the absolute value of a minus b equals 2. So our answer is 2. Let's summarize what we've learned in this problem. We started with the equation a plus b equals 3,598. Through a series of algebraic manipulations, we factored the left side to get the quantity 1 plus a times the quantity 1 plus b equals 3,599. The key insight was recognizing that 3,599 can be written as 60 squared minus 1, which factors as 59 times 61. This led us to two possible cases for a and b, but both resulted in the absolute value of a minus b equaling 2. Try to apply these factoring techniques to other similar problems to build your algebraic intuition. Welcome to this math video, where we'll learn a clever technique for mentally calculating squares of numbers. This method uses a special identity that allows us to compute squares quickly by choosing values that make our calculations easier. Let's start by looking at the identity we'll be using. The identity states that a squared equals the product of a plus b, and a minus b plus b squared. This identity works for any value of b, but we'll choose b strategically to make our calculations easier. The trick is to choose b so that a plus b and a minus b are round numbers that are easy to multiply. Let's look at our first example. We want to compute 63 squared. Following our strategy, we'll choose b equal to 3. Now, let's substitute into our identity. We get 63 squared equals 63 plus 3 times 63 minus 3 plus 3 squared. This simplifies to 66 times 60 plus 9. 66 times 60 is 3,960. Adding 9 gives us the final answer, 3,969. Let's try another example. We want to compute 18 squared. For this case, let's choose b equal to 2. Substituting into our identity, we get 18 squared equals 18 plus 2 times 18 minus 2 plus 2 squared. This simplifies to 20 times 16 plus 4. 20 times 16 is 320. Adding 4 gives us our answer, 324. Let's move on to our third example. We want to compute 54 squared. For this case, we'll choose b equal to 4. Substituting into our identity, we get 54 squared equals 54 plus 4 times 54 minus 4 plus 4 squared. This simplifies to 58 times 50 plus 16. 58 times 50 is 2,900. Adding 16 gives us our final answer, 2,916. Let's try a more challenging example. We want to compute 988 squared. For this case, we'll choose b equal to 12. Before I continue, can you think about why 12 is a good choice for b in this case? With b equal to 12, a plus b becomes 1,000, which makes the multiplication much easier. Substituting into our identity, we get 988 squared equals 988 plus 12 times 988 minus 12 plus 12 squared. This simplifies to 1,000 times 976 plus 144. 1,000 times 976 is 976,000. Adding 144 gives us our final answer, 976,144. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.